Okay, this is section 3.6, but before I erase this, Savannah, this is number what? This is on section 3.4, number what? 35, and this one box is 38. If you want to pause it right here, if you had trouble with those, you can take a look at this. If you have any questions, you can ask me in class. Anyway, I'm erasing now. All right, section 3.6, people, it's called the chain rules, one of the most important rules, and it's also one of the most forgotten. Do not forget the chain rule or the product rule. People don't forget the quotient rule because as soon as you encounter it, it's got a quotient. You go, oh yeah. But with product and chain rule, people always forget. It's very strange how that works out, especially with trig functions. Anyway, do you know how to take derivatives of things that are added and subtracted? At least what you've encountered so far. If you've got three things that are added together, how do you take the derivative of that?
This plus this plus this.
The answer is one at a time, which is what you were trying to indicate. If you're adding and subtracting things, you consider it one term at a time and possibly apply the product rule if there's in that term, the product or the quotient rule or the power rule, whatever. But you apply those to them one term at a time. So when you're adding and subtracting, you take them one piece at a time. If you're multiplying two things together, you have a product rule. First times the derivative of the second plus second times the derivative of the first. If you're dividing two things, you apply the quotient rule, bottom times the derivative of the top, minus top times the derivative of the bottom over the bottom squared. And so we've taken care of when we have addition, subtraction, multiplication, division. What's the other thing that we do with functions? Yes, and we need a rule for compositions, and that's called the chain rule. Okay, and the chain can have many, many, many links. Quite often, they only have what we call two links of chain. I'm going to give you an exercise to do where the last one has 7. It's going to be so fun. You're going to love it. It's like putting a puzzle together. It's pretty fun. Here's the deal, though, and I want to put this on the board and see if we can come up with it on our own. If we have, for example, 9x to the 4th plus 6x squared plus 1, if that's what y is, we already know how to find that derivative, right? What is it? Okay, now I want you to consider this because I'm trying to teach you something new. Does this thing factor? No. Yes, it does. The answer is yes. I would not ask you that if it didn't. So what's another name for this y? Here, if I factor it, it's going to factor into...
This is the last call for anyone that needs to have a retake picture taken.
Obviously, this is going to be 1 and 1, right? What's going to be up here, do you think? Did that give you the 6x squared in the middle? Oh, these are squared.
Yeah.
Plus on both. So another name for this would be 3x squared plus 1 squared, right? Now, I know, and I know that you know, that if you were presented with a problem this way, I know that you could square this out and do this to it. And I encourage that. That's great. That's not the point. What we want to do is try to figure out how to take the derivative of it from this form and still get this answer.
Product rule.
Yes, that would work. That's not what we're going to do, though.
Chain rule. Yes.
Chain rule, but do we know what it is yet? If you already know what it is, don't be telling everyone else. How can we manipulate this as a derivative to finally end up with this, do you think? What do your instincts tell you to do?
Compose. Can you decompose it? Use the power rule on the entire thing.
I think that's a good place to try to investigate. So what would it look like?
Oh, never mind. 2 parentheses 3x squared plus 1.
To the 1, right? Which we're not going to bother to write. If that were the case, then it would be 6x squared plus 2. That's not what this is.
You can't do that. No. What if you do that?
So that's not all. But I am going to tell you that is part of it. not inside necessarily, but it's going to be times, and it's because you don't know this yet, but it's going to be times this guy's derivative, which is what?
6x.
Because look, this was 6x squared plus 2. We needed this to be 6 times bigger and this one more big. This needed to be 6 times bigger and add an x to it. That's what 6x does for you. It improves that. So what we're really distributing here is 12x, which would give us 36x to the third plus 12x. So the moral of this story is, when you're doing a chain rule with composed functions, and by the way, believe it or not, this thing is a composed function. It's 3x squared plus 1 stuffed into x squared. Right? Let me show you that it's composed. If I let f of x equal x squared and g of x equal 3x squared plus 1, then f of g of x says to stuff this in for all the x's in f, and that gives you 3x squared plus 1 squared. So it is a composed function. And notice what we did. We took the derivative of f, that was this guy right here. Remember, f is composed of 3x squared plus 1. But f, which I call the macro function or the big function, the big thing going on here is this squaring right here. So we applied the power rule to the big thing. Then you multiply by that guy inside, the derivative of the one inside of g. Yes.
Does it matter how you compose it?
Yes, it does.
Matter.
Yes. So if our function, if we call this function y, that we're calling y right here, we actually call it f of g of x, delineating the two different things going on, then what we did is we took f prime of g of x, that's this, times g prime of x, that's this. So you take the derivative of the outside and multiply it times the derivative of the inside. Micro, kind of. We'll do several more. I know this is a brand spanking new idea. We'll do several more so you can get used to it.
Derivative of the outside times derivative of the inside.
Yes, but when you take the derivative of the outside, you keep the inside whole. You keep it without messing with it, and then you multiply by the derivative of the inside part. That's how you handle composed functions as a derivative. Yes.
We try composing it differently in school.
What do you mean?
Like if you did f of x equals x plus 1 squared, and then g of x equals 3x squared.
That would still work.
It would still
Yeah. I misunderstood your question. But the key is this, folks. This is the chain rule written in function notation. Now, here is the chain rule written in derivative notation. If you have y, y written in terms of x, so y's got some x's in here, x's strung out here, then the derivative of y with respect to x is equal to the derivative of y with respect to u times the derivative of u with respect to x if u is the function that has been stuffed in.
That made even less sense than the function notation.
What?
That made even less sense than the function notation, which I didn't think was possible.
Okay.
Welcome to calculus.
This right here, Connor, this right here, in this notation down here, this is u.
All right.
So if y equals u squared, think about this. And remember, u is a function of its own. It's a function written in terms of x. So if I have y equals u squared, understanding that this is some function of x, but I don't want to pay attention to it yet, then if I were taking the derivative, it would be the derivative of y with respect to u. Because it's written in terms of u, which would be 2u, yeah? But u itself is a function written in x, so u is equal to something with x's in it. So that means if I'm going to apply the chain rule, I'm going to have to take dy with the derivative of y with respect to u, which gives me this, times the derivative of u with respect to x.
It makes sense until the du dx.
Okay, remember, u is this thing right here written in terms of x.
Yeah.
And the derivative of this is the derivative of u, this is u. U equals, see, u equals, I'll put it up there. U equals 3x squared plus 1. So du dx equals the 6x that we got right there. That's du dx. And I did this wrong. This should be dy dx. The entire derivative of y with respect to x is the derivative of u. Sorry. The derivative of, dy dx is the derivative of y with respect to u, which is this, times the derivative of u with respect to x. We're getting inside.
I think I'm starting to.
Okay, you'll see more and more and more of it. Okay, so this is another expression of the chain rule. Okay, most people, because you're used to this kind of notation and you understand this better, you've been dealing with it longer, most people understand this one better than this one. I don't care which one you really think about, but sometimes you will see this and you got to understand they're talking about the chain rule. Sometimes you'll see it written like this, because this is calculus notation, which you're not as comfortable with. All right, now let's practice with this, shall we? See if we can make it happen.
Yep, left.
In the 10 box at the top of page 149, they have this written in the calculus notation. But in the box at the top of, it's not even a box though, in a statement at the very top of page 150, you see the one that I wrote up here, which most people like better. The reason you didn't box that up is because it's not calculus. Actually, this is function notation, which you learned before. This is calculus notation, and they mean the same thing. All right, so going to erase this, and we're going to see if we can, it's called the inside or the outside inside rule. That's what we're going to practice. That's how most people learn it because they're more familiar with this idea, with the way it's written.
Outside, inside rule.
Outside, inside. So we take the derivative of the big guy times the derivative of the little guy. Big guy, little guy. And when you're taking the derivative of the big guy, the little guy stays intact. It doesn't mess with them. It just is thought of as a single thought. Okay, so let's take a look at example 3. It says, an object moves along, oh, here we go again. An object moves along the x-axis so that the position at any time greater than 0, greater than or equal to, is given by cosine t squared plus 1. And notice what they do here. They call this x of t. Why would they do that?
Because I hate this.
No, there's a reason. Well, that's why the t is there. But why do they call it x of t?
Because it's position along that x-axis.
Yeah, because it's moving on the x-axis. It's position on the x, so that's why they refer to x. Okay, so the question asks, though, let's see, they give us the information, says find the velocity of the object. Even though this isn't s, because it's moving along the x-axis, they called it x, it's still a position function with respect to time. So if I want to find a velocity function, what do? Derive it. So we want to derive x of t, and we'll call it x prime of t. And I don't know if you can see it or not, but this is going to require the chain rule. This is cosine of x for our macro function of t squared plus 1 for our micro function. So what do we have to take the derivative of first? Cosine, which is what? Negative sine of what?
T squared plus 1.
T squared plus 1, because in the first derivative, the stuffed-in function stays intact. You don't mess with this. You're deriving cosine. Cosine of what? I mean, the derivative of cosine of what? Whatever you are cosigning. It becomes the negative sign of that very same thing, and then times, which is 2t. And so to write it in a customary, agreed upon way, we should put that in the front. So it's going to be negative 2t sine of t squared plus 1. And this is our velocity function for this particle using the chain rule, because we've got a polynomial stuffed into a cosine. Since you've got a composed function, you have to use the chain rule. You see how that worked? So you focus on the derivative of cosine first. And people always say, well, it's the cosine of 2t. No, you're doing two things at once. Just derive the cosine. And whatever it was cosigning, that's what you're signing here. Then focus on this derivative and it becomes multiplied by that. So don't try to do two things at once. That's another hang up when people first encounter this. Okay. So next one just says differentiate, which means perform the derivative. And if I come over here, have I got room? I think I do. Can somebody read me what we're deriving in example 4? What do we got to begin with?
Sine
X squared plus 6?
x.
X squared plus X.
X.
Like that?
Yes.
Okay. So what's y prime going to be applying the chain rule?
Cosine
X
x squared plus x.
Good. Times
2x.
2x plus 1. We got both of these. So to write it, I mean, you can leave it like that. That's fine. But most people will put this out front together as a single thought times the cosine of x squared plus x. Why do we do that? Why do we put stuff out in front of a trig function? It looks better because if we leave it like this, the question sometimes in people's minds, because people tend to be sloppy,
Are we
is
cosigning?
are we cosigning this and multiplying that result times this, or are we multiplying that and then cosigning the result? Can you see how it could be ambiguous? This is not ambiguous. It's this polynomial times the cosine of this polynomial. That's why we stick it out front.
Should we do product on that?
If you want to take the next derivative, you would. But we're not. We just wanted the first derivative using the chain rule. That was done.
Oh, lines. Yeah.
And then if we wanted the second derivative, then yes, we would apply the product rule to this. And the chain rule again. You want to do that?
No.
Just for the fun of it?
Okay. No, we're good. We can do it.
I don't see why not.
Yeah, why not?
Yeah, let's do it.
Okay.
Why not? Why not?
Let's say we wanted the second derivative of this. This is y prime. We may have bit off more than we can chew, but if we want derivative, then we would have to apply the product rule, which would be what?
2x plus 1.
Good.
2x plus 1 times the derivative of that one.
Negative sine of x squared plus x
Yeah, times 2x plus 1. Plus.
That's just the first times the derivative of the second, using the chain rule on the second. Plus
The cosine. Okay. Cosine of x squared plus x. 2. Just times 2. Yeah. Boom.
and then if you had to go one step, and you should go one step further, and that's to distribute this through there, and it would look like this. Don't let it bother you. Think of that as a single thought. It's going to be negative, this negative right here, 2x plus 1 sine of x squared plus x. Oh, this is squared. That's what it is. You get 2x plus 1 times 2x plus 1. There's 3 things being multiplied, and this times this is just this squared. Plus 2 cosine x squared plus x. And that would be your acceleration function for this.
Wow.
So product rule and chain rule combined together. Okay. All right. That was a good thing to do. That was fun.
Yeah.
Okay. Now let's take a look at example 5, because now we're going to do a 3-link chain. Everything we've done so far has been a 2-link. So, can somebody please read me the function we got to derive?
G of t equals the tangent of 5 minus sine of 2t.
What's that?
5 minus sine of 2t.
I assume that the 2t belongs to the entire sign, right?
Yeah.
Can you see the 3 pieces of chain here? The 3 links? We will have to derive tangent. We will have to derive this. And we will have to derive this. It's like f of g of h. F would be tangent of x. G would be 5 minus sine of something. And h would be 2t. We have three chain link here. Okay, so g prime of t is going to be, first derive the biggest thing you see, the biggest thing going on, which would be what? Yes, tangent's the biggest thing. What's its derivative? Secant squared of what? Of that. That does not change. Only this gets derived. times. What's the derivative of this stuff now?
Negative cosine.
Negative cosine of what? 2t. Times the derivative of this, which is 2. There's your three link chain.
That's all it is?
Yeah.
You just start from outside and work your way in.
Yeah.
You just derive.
And so, apply those things together, it would be a negative 2 secant squared.
Wait, what?
I could put the cosine there. I'm multiplying it together. I'm cleaning it up.
Yeah, okay.
This negative times this 2 is negative 2, and then I'm going to put this next times this one. And you don't have to do any more than that, but it's kind of nice to take out the ambiguity. Okay? Did you follow that? You see why it was 3 chains? 3 pieces of chain?
Okay, now let's do that one.
Now let's find its others.
We're not deriving that one, no.
Another 2 chain one.
Another 3 chain one?
Yes, there.
No, you'll have a chance to do up to 7. You'll get a practice. Lot of practice. Okay, 2 more things. Do you remember I told you that we're studying parametric equations in here? Well, we are a little bit. Do you remember what parametric equations are?
We're done line.
Yes.
Yeah.
I know.
What is a parametric equation and what is involved? What does it look like when you write it?
T's.
It involves an x and a y in a single equation. Well, an x equation and a y equation, both written in terms of t, and together they make a parametric equation. Together. Do you remember that at all?
Yes.
Yeah.
Those are fun.
Okay. If you have a parametric equation, then you need to memorize this. It would be a really good thing to box up in red again. So parametric equations, get it straight. And you will be quizzed and tested on this.
Oh.
So if you are given a function as a parametric equation, and we'll discuss what that means again in just a minute, then the derivative, okay, so you'll get, parametric equations look like this. X of t equals something, y of t equals something, and the 2 of them together form points on this grid, both of them dependent upon a t value called a parameter. So this x of t will have t's in it, this y of t will have t's in it. And the derivative, and by the way, as I told you before, it's gonna generate, if we plug a t into whatever x is equal to and a t into y, the very same t, then it will give us a point, an xy point to plot on that grid. And if you string all the points that are plottable on that grid together to make a function, then that curve's got slopes to it. So, and because it's an xy, it's a bunch of xy points together, then we want to find the derivative of y with respect to x. And what that is the derivative of y with respect to t divided by the derivative of x with respect to t. It is not the quotient rule. When you want to find dy dx, the derivative of y with respect to x on the curve generated by these points, then you find the derivative of this one and divide it by the derivative of this one to get the derivative of y with respect to x. Okay, now take a look at example 6. It says, find the tangent to the right-hand parabola branch defined parametrically by, and you'll notice you have x equals secant, that has a t in it, and y equals tangent with a t in it, but only between negative pi halves and pi halves. Okay, so they're restricting our domain. So this is our parametric equation. X equals, what did I say, secant? Is that right?
Yeah.
Secant t, and y equals tangent. So there's our parametric equation, those two things, those two pieces. Well, remember that we're between negative pi halves and pi halves when we go to plug something in. And it says, at the point root 2, 1. In any other problem that I've ever seen with parametrics, they never give you the point. They don't give you any of it. None of it. They just will say this. Find the tangent line to this curve when t is pi fourths. They do not give that point. So in my book, I have it scribbled out. They will not give you the point. They did in this example, and I think it's bad because they won't give it to you in the exercises. So let's pretend they did not give us that point. It just says, find the equation of the tangent line to this parametric equation when t is pi fourths. So what do? We have to find, in order to write the equation of a tangent line, we need a point and we need a slope. We all know that. Those are the two things we need, and we don't have either one. We don't even have a piece of the point, not in this case. All we have is a value of the parameter, pi fourths. But because of that, and because we have an x and a y, we can find the point we need by plugging in pi fourths to this. That will give us the x coordinate of the point. And by plugging pi fourths into this, and that will give us the y coordinate of the point. I haven't done any deriving or anything yet. I haven't even gone after my slope. I'm just trying to find the point. And I need an x value and a y value. And all I have is a t, but it's enough. Can anybody tell me what they believe the secant of pi fourths is in exact form? That means you got to remember your trig.
What the secant of pi fourths is.
Yeah. What's another way to write secant? 1 over cosine. So this is really what I want to do, right?
Is it 2 over?
It's just root 2. It's root 2.
This is root 2 over 2. But 1 over root 2 over 2 is, you're right, it's just root 2.
2 over root 2.
It's 2 over root 2, but we don't like that form, so we rationalize the denominator and we get 2 root 2 over 2, and they cancel. So it's root 2. That's where they're getting the root 2 from that they provided you with, but they usually won't do that. You have to find it yourself. Okay? We also have to evaluate y when t is pi fourths. What's the tangent of pi fourths? 1. Because at pi fourths, you've got both legs the same length, and the tangent is 1. So there's our point. That's one of the things we needed to write the equation of a tangent line. In calculus, when we're looking for a slope, what should we do? Derive, which means we need a formula for derivative in a parametric situation. And this is it. You look at the y value. So what I'm saying, dy dx, there's no t's in this. Dy dx, well, there's over here, that's what we're going to do. But dy dx, which is what we want the slope of this curve generated by these xy's. We want the slope of that curve, which is this. And it's going to be the derivative of this with respect to t, which would be what? Secant squared of t over, what's the derivative of x with respect to t? Secant tangent? See, it's not the quotient rule. And that's what people get, they sucker for this. They say, well, that's a quotient. I'm going to apply the quotient rule because I'm trying to find a derivative. No. It's the derivative of the top over the derivative of the bottom, which is what you guys all wanted to do before I gave you the quotient rule. You take the derivative of the top with respect to t, the derivative of the bottom with respect to t, and you evaluate that derivative at that t. Just like we did these guys. It's all in terms of t, this parameter. However, we can reduce it a bit. What was the secant of t again? I got them right there. They designed this very well. What was the secant of t?
Cosine, maybe not.
No, I'm not deriving.
Oh, secant of that.
It's root 2. That's what so we have root 2 over, and the thing that's left down here is tangent, and what is that? 1. So the derivative is also root 2. This was a nicely designed problem that would come out pretty. Did y'all see what we did? Here's the derivative. Now we're evaluating the derivative at this t value, which, by the way, is between negative pi halves and pi halves. That's what they told us, the stipulation they gave us. So now I have a slope and a point, and now we go back to Algebra 1 skills with radicals. So the equation of the tangent line, not tan, but tangent line, is going to be y equals okay, root 2 times x. By the way, if you're like the Germans and you want to put the coefficient in front of x, then you put a hook here so that you're sure that the x is not inside. Or you put the x in the front of the root 2 for the same reason we discussed earlier. I'm going to leave it like that. Minus
2.
plus 1, which is, now I'm going to write it like this, x root 2 minus 1. Probably still want to put the hook there so you know that that minus 1 is in there. That's probably not quite as big an issue, but this is the equation of the tangent to this parametric curve when t is pi fourths. You have to go find your own point, all of it. You have to go find your own slope by remembering this idea here. It's the derivative of the top over the derivative of the bottom with respect to t. Anybody not follow what we did there? Any question about that at all? Okay, I want to do example 7 with you, and then talk to you about example 8 for just a minute, and then we'll be done. That's it. Doing pretty well. Okay, example 7. Find the slope of the line that's tangent to the curve y equals sine to the 5th x at a point where pi or x equals pi thirds. Find the slope of a tangent line to a curve at a point where they give you the x value. And we're also going to show that the slope of every line that's tangent to this other curve is positive. First one, having to do with y equals sine to the 5th x. Find the slope of the line tangent to the curve y equals sine to the 5th x when x is pi thirds.
So we find the derivative.
Yes. Don't look at the solution. I'm about to show you something that people stumble on routinely, so pay attention and don't stumble. I should have left that up there. That should have been boxed up in red. Hopefully you can find it again. So I have the equation. Do they call it y equals? Yeah. Okay. So it's y equals sine to the 5th x, and we want to evaluate that derivative when x is pi thirds. Okay, so that means we're trying to find the slope of the line tangent at x equals pi thirds. We need a, as Jacob said, a what? What are we going to have to do? Derivative. What's the derivative of this?
Can we just split it up into 5 different signs? And then find out?
Apply the product rule in 5 different ways? I wouldn't.
Can we just split it once?
I wouldn't.
Well,
How would you begin? Okay, and the power rule would give us what? 5.
sine.
Sine to the 4th x. This is the killer. This is the part everyone forgets. Times cosine.
That makes sense.
I'm glad it does, because it doesn't for a lot of people. I can tell by Connor's face it doesn't yet. Maybe it's coming around. Here's the problem, folks. It's the way that we write sine to the 5th. Because it's quicker and easier to write it this way. We always put a little 5 right here, but it causes us to forget this is actually a composed function. This is what it really means. Right?
Okay.
It's a little easier to see now because we bring the 5 down around front right there. We reduce that to 4, put it where we're used to seeing it, but then we have to multiply by the derivative of the inside, and the inside is sine x, which is whose derivative is cosine. So it's actually a chain rule. But when we write our trig functions this way, people always forget because all they see is the power. They usually get this right. But then there is an inside function. You have to derive sine also. Do you see where you could stumble? Whenever you see an equation like this that you have to derive, it would be a good habit to scoop it in parentheses out here. You'll remember things better. It's up to you. Just don't forget, this is a composed function where we have to take the derivative of sine as well and use the chain rule. So now I want to evaluate y prime at pi thirds, which is going to be 5 times the sine of pi thirds to the 4th. The reason I'm doing that is because I want to find the sine by itself, and then whatever I get, I'm going to 4th power it, times the cosine of pi thirds. Now you got to remember your trig. Do you remember the sign, how to label a stand-up, because pi thirds is 60 degrees, a stand-up triangle? Do you remember how to label it?
Square root 3 over 2.
This is 1, this is root 3 over 2 because it's the long leg, and this is 1/2. And if you have this looking at you, if you take the time to draw this, you'll be able to get these things. What's the sign of pi thirds?
Root 3 over 2.
Root 3 over 2.
Yeah, good job, guys.
To the 4th. What's the cosine of pi thirds?
1/2.
Can I do that?
No.
Sure.
Is that okay?
Yes.
Now, what is root 3 over 2 raised to the 4th?
4.5.
I don't want to know the decimals. 9 halves. 4, 5 halves times. You see where he's getting 9 halves?
Yeah.
If you square this, you get 3.
Yeah.
If you square that, you get 9. But if you square all of that, you get, is it fourths?
Oh, do we want to do that?
You have to square the numerator and denominator when you square a
Yeah,
fraction.
we do.
I mean, fourth power fraction.
Oh, so it's like
9.
64. 2 times 4 negative 16. 32.
I'm so down.
I forgot how these work.
2, 4, 8, 16. You're right.
Is there anybody who did not follow that? You okay on this, Axel? Yeah? Connor? Okay, that's the slope of the line. Barely, it's a little bit more than 1. The slope of the line of this curve when x is pi thirds. Okay? Leans to the right slightly more than 1. It's not a really steep line. Okay, the last thing, oh no, there's one more part of this. B part. It says show that the slope of every line that is tangent to 1 over 1 minus 2x, close it to the third, is positive. That kind of seems like a tall order to show that every slope is, but it's not that bad. What was the function? Y equals what? What was it?
1 over 1 minus 2x.
All of it.
And the entire denominator is
All to the what?
third.
Third. Okay, so if we want to talk about slopes at all, we need a derivative. What's the derivative of this thing?
Well,
I'm not going to do the derivative yet. Is there a better name for this that we can rename it so that it's easier to handle?
1 minus 2x and negative.
That would be a little easier to handle. Do you all understand that? That would be an easier thing because we can apply the power rule. And so it would be y prime of that's going to be
Negative 2, 3, 1 minus 2x to the negative 4.
Yeah.
That's how it works. Times negative 2.
Here's your chain rule. Don't forget it.
Okay.
So we end up with 6 over 1 minus 2x to the 4th. Yeah? That seem reasonable?
Yeah.
Is the numerator positive?
Yeah.
Is the denominator positive?
Yeah.
All the time?
Yeah.
Is your 4th powering. So this slope generator will always generate a positive slope. This fraction is always positive. And you don't have to really say why. You just say the numerator is positive, the denominator is positive, so the fraction is always positive. Therefore, the slope is always positive.
So what if you kept the thing in the denominator, but then you did like power rule?
Not power rule, quotient rule.
Oh,
That would be your only option. And it would work. Do you want me to show you?
nah, I
Oh.
was just thinking like, because if you did like the power rule, then like subtract it down to.
Right. And it would be kind of looking, but you would have, what you really be required to, if you didn't move that up to this form, if you did this, your quotient rule is your only option.
I was thinking you could do the power rule, but I guess not. So yeah.
Okay? You can do the power rule if you rename it properly. Okay. Last thing, this example 8, and whether you buy this argument or understand it fully or not, I hope you come away with understanding that whenever we do trig in this class, it will always be in radians, never degrees, because here's what would happen. Just a quick brief overview of what would happen. It is important to remember that the formulas for derivatives of both sine and cosine were obtained under the assumption that x is measured in radians, not degrees. The chain rule gives us new insight into the difference between the two. Since 180 degrees is equal to pi, then x degrees is equal to pi x over 180. That was your conversion factor that we learned in trig. So by the chain rule, the derivative of sine x in degrees would be the derivative of sine pi x over 180 in radians. And to do that, you've got a chain rule where the derivative of the inside would be pi over 180. So you take the derivative of sine, you get cosine of pi x over 180 times the derivative of the inside, which is pi over 180, and you end up with pi over 180 cosine of x in degrees. The factor pi over 180, which is annoying in the first derivative, would compound repeated differentiation. So if we wanted to find the fourth derivative, we'd have to use that pi over 180 4 times, and the number would get out of control. We'd have pi to the 4th over 180 to the 4th, which is ridiculous. Okay? We see at a glance the compelling reason for the use of radian measure. The radian measure is the blue one. In degrees, the same sort of thing. If you put the same thing in degrees, you'd have the red one. And you'd be trying to find the slope of that red one at different locations, where it's a lot easier to find the slope of the blue one because it's more spread out. You see what I'm saying? So if that was not convincing, accept the fact that all of our angles will be measured in radians in this class.
That's all that example was trying to show.
What's that?
That's all that example was trying to show.
Yes, they're just trying to give you an argument for why radians is much better to do calculus with than degrees, that's all. Okay? All right, so the assignment is given. If you have any questions in class, Savannah, ask me. I'm going to cut this off now, so good luck. See ya.
Limited power.